Hello everyone, my name is Stefan, and now let's bring some radio data into our flow graph by adding a source block. Now to start, we will locate and add a file source to our workspace. This block allows you to use a file as the radio data input for your flow graph, which means you won't need an SDR hardware to proceed. This file here contains raw radio data captured from a real airwaves by an SDR enthusiast and saved for later use. If you were building a fully functional radio receiver, you would use a different source block designed to connect with your SDR hardware. That block will provide a real-time radio data directly from the airwaves. Next, we will configure the file source block. Double-click on the block to open its properties. In the File field, click the three dots and navigate to the project files you've downloaded earlier from the resources section of this course. I will also share it on my website. And we have selected the file named 2024 AM example typhoonix.iq file. You might notice a warning at the bottom of the properties window saying the port isn't connected. Don't worry about this for now. We will address it shortly. At this stage, your property window should look similar to this. Once everything is set, we will click on OK to close the window and return to the workspace. And this is a good point to save your work. Press Ctrl S or go to File, Save. So you can use any valid Linux file name, but let's actually call it, let's say, first AM example or first AM receiver. That's it here. Now, when working in flow graphs, remember to save early and save often. This ensures you don't lose progress if something unexpected happens. From this point on, I will assume we are familiar with the basic steps for adding blocks, accessing their properties, and configuring their values. So instead of spelling out every action, we will focus on explaining what each block does and how it fits into flow graph. Let's move ahead and continue building. Now that we have set the file source, let's move on adding to blocks that will process the radio signal. Don't worry too much about understanding every detail just yet. We will delve into how these blocks works in later sections. For now, the goal is to assemble the functioning flow graph. Now we will start by adding a signal source to your workspace. This block generates a continuously repeating sequence of values that represent a sinusoidal waveform. Now double-click on the signal source block to open its properties window. Now for the frequency property, instead of entering fixed number, type center frag minus, oops, also we need to change this to center frag. Now here signal source center frag minus frequency here and here. Now you can see, let's open again, what just happened here. Instead of putting input a static value, you enter the mathematical expression involving variables, the center frag and frag. In fact, GNU Radio Companion allows you to use almost any valid Python expression for block properties. This feature is incredibly powerful and will make your flow graphs much more flexible. In this case, the frequency of the signal source is determined dynamically by subtracting the value of the block with the ID frag from the value of the block with ID centerFrag. After clicking OK, you will return to workspace. Notice something interesting. The block no longer displays the mathematical expression you entered, which this needs to be 900. I forgot to save the work. Now, here, the block no longer displays the mathematical expressions you entered, right, like this. Instead, it shows the calculated result based on the current values of centerFrag and frag. And again, in the workspace, you'll notice that the signal source block's frequency is displayed as 20 key or 20,000. This value comes from the calculation of centerFrag subtract by frag. With the default values we set earlier, centerFrag is 900,000 and frag is 880,000. So the result of this subtraction gives us 20,000, which is exactly what we are looking for. Next, it is time to add multiply block to the flow graph. This block will combine the outputs of our two sources. It is important to be careful here and ensure that you select the correct multiply block, as there are several blocks with similar names in the GNU Radio Companion library. Now, to connect the blocks, as you can see here, we need to get multiply here. So to connect the blocks, simply click the output port of the first block, such as one of sources, and then click the input port of the multiply block. You can also click in reverse order. The connection will work either way. When connecting the inputs to the multiply block, pay attention to labels next to the input ports. You will see in0 and in1 labels. These are the ports where you will connect your sources. In general, the inputs are on the left and outputs are on the right. But be aware that some blocks may be rotated. Once the connections are made, your flow graph should look like this. As you continue adding and connecting blocks, it is a good practice to take a moment to tidy up the flow graph layout. This helps with readability, especially as the flow graph gets more complex. You can click and drag blocks to reposition them. And notice that the connections between blocks are sticky. So they will follow along as you move the blocks. So while organizing the flow graph isn't strictly necessary, to be honest, it makes them much easier to follow and understand. Now, let's proceed by adding low pass filter block. Now, this type of filter is essential in many radio signal processing workflows because it removes or reduces unwanted frequencies. Filters like this will be explored in more detail in section 6. But for now, configure the low pass filter block by setting the cutoff frag to 5E3, which is 5000, and transition width to 1E3, which is 1000, leaving all other properties as defaults. Now, once this is set up, connect the input of the low pass filter to the output of the multiply block. After doing so, your workflow should look like this. So by following these steps, you will have successfully proceeded the signal with multiplier and filter, which is fundamental technique for many signal processing tasks in SDR applications. At this stage, you may notice that the low-pass filter block's label appears in red. This happens because GNU Radio Companion actively checks your flow graph for errors as you build it. When a block has an illegal condition, its label turns red, indicating there's an issue. In this case, the problem is that the output of the low-pass filter isn't connected to anything. It is important to pay attention to these visual cues as they help you catch issues before running the flow graph. Other common causes for red labels include missing or invalid properties or connecting multiple outputs to a single input. Now, let's add AM demode block. This block will perform the critical function of demodulating the incoming radio signal, effectively extracting the audio signal that we can listen to. You can configure the AM demode block by setting its channel rate to the value of samp rate and it is audio decimation to 1. After configuring the block, you will need to connect its input to the output of the low pass filter block. When connected, your workload should appear like this. The AM demode block will now be responsible for translating the raw radio signal into something audible, allowing us to extract the audio content from the AM broadcast. So we will delve into specific of how the AM demode block operates in next sections, but for now it is essential to recognize its role in the overall system. As you continue building the flow graph, there's an important detail you should be aware of when connecting blocks. The input and output ports of each block are color-coded. For instance, the AM demode block's input port is blue, like the rest of them, while output port is orange. These colors are meaningful. They indicate that the type of data flowing through the ports. So blue ports handle complex numbers, while orange ports handle floating point numbers. At this point, we are not diving into the complexities of complex numbers, but it is important to remember this rule. Connections can only be made between ports of the same color. So if you try to connect an orange port to a blue one, the flow graph will signal an error, typically turning the connection to red. Keep this in mind as you progress. Now that we have addressed the color coding issue, let's move on to adding the rational resampler. This block plays a crucial role in adjusting the sample rate of the audio signal, ensuring it matches the requirements of your sound card. So we will set its interpolation to 32 and its decimation to 400. Once you've configured the block, connect its input to the output of AM demode block. Initially, you may notice a red arrow appear between these two blocks, indicating that something is wrong, obviously. So the issue stems from trying to connect ports of different colors, orange and blue. Just as we mentioned earlier, this is similar to trying to pass an integer where a string is expected in programming. To fix this, we will open the rational resample block's properties and change the type from complex to float to float. Real taps. After doing so, click OK, and the ports of the rational resampler block will now turn orange, and the red arrow indicating the invalid connection will change to black arrow as normal, confirming that the connection is valid. At this stage, we are very close to completing the flow graph. We have set up the sources, applied several processing blocks, and resolved the issue with the port color mismatch. However, we still need to consider one last thing. What are we going to do with the processed data? Right now, all the data flows through the blocks. Um, but we need a sink to output the final result. So we will learn that in next lecture.